chapter 13.7 to 13.8, this involves Kepler's laws and satellites. And so Kepler's laws, the first law is the law of orbits, the fact that the planets are moving around in an ellipse. And this was the thing, by the way, historically, that really solved the problem of the planets. Since the time of Ptolemy, they had circular orbits for the planets, and all the planets are going around the Earth. And they kept finding these problems in the predictions that this model made. And some people tried to solve it by putting the sun at the center, right? Copernicus, Galileo, they had put the sun at the center, but that didn't solve the problem of the planets. There was still this problem where the movement wasn't quite right. The thing that actually solved the problem of planets and their orbits was this, the fact that they were ellipses, not perfect circles. So that's Kepler's first law. The second law says that as a planet moves around its orbit, it sweeps out equal area in equal times. So the area here, and this time, if I take that same time for it to move this way, and here it's moving faster, time 1 is equal to time 2, and if those two things are equal, then these areas are equal. But the third one is that the square of the period is proportional to the cube of the semi-major axis. And so if we're not dealing with circles, we're dealing with ellipses, then we no longer have a radius. Instead, we have this thing with two centers, so to speak. The semi-major axis, here's the major axis, right? Major means larger. So an ellipse has two axes, this one and this one. And then half of that, this is the semi-major axis because it's half. This is A, right, the whole thing. Then this is 1/2 of that. So 1/2 A is the semi-major axis, the distance from the center of this line to the edge. Okay. And it looks like this. The square of the period is proportional to the cube of the semi-major axis. So A is actually semi-major axis. It's this. In common notation. Okay. And so here's one application of this. We have the conservation of angular momentum. I initial, omega initial equals I final times omega final. But we're dealing with the same object, right? It's a point particle that's moving around. So this is mr squared omega initial is equal to mr squared. So this is some final, some different radius, omega final. But omega is Vr, right? So this is mr squared Vr, I'll call Vi, equals mr squared V final, over R. Vi over R, and then Vf over R. So that cancels out with that. M's cancel out. And I'm left with this. R Vi equals R Vf. Conservation of angular momentum, which is, and really, right, what are we looking at here? This is one of the laws that we can use. It tells us that if I'm closer, then I have a smaller or higher velocity, and if I get farther away, if R gets bigger, then V has to decrease. So R and V are inversely proportional. The closer you are, the faster you move. The farther away you are, the slower you move. Okay. Another application here. So if we have the force is equal to the mass times the centripetal acceleration, right? And so F, the force though, is given by gmm over r squared, and the centripetal acceleration is given by v squared over r. Right? But what is v? V is 2 pi r over t over the period. So when I plug this into here, I get g, I'll cancel out the m's, m over r squared equals this thing, 2 pi r over t squared over r. So now I have gm over r squared equals 4 pi squared r squared over t squared r. So one of these cancels out with one of these. And then I'm going to multiply t squared over there, so I get t squared equals, I'm going to have 4 pi squared over gm. And now on this side, I'm going to have r cubed. And so you see, the square of the period is proportional to the cube of the radius, in this case, since we're talking about a circle. And so you can see how from Newton's law, we can get this law of Kepler's. This is Kepler's third law. Historically, it was the other way around. Kepler developed this law before Newton's time. And this was one of the reasons that Newton's laws started to be accepted, because it still didn't make any sense that objects could exert a force on each other from vast distances. But this matched Kepler's third law. It works. Application number 3 is just taking what we looked at and then applying it to multiple bodies. If I have different objects going around the same object, that means that I can write, t squared over r cubed is equal to 4 pi squared over gm. This is the same. Like if this is the sun, for example, this is the same. So that means this ratio should work for any planet. And so that means for planet 1, that is equal to the same ratio for planet 2. And again, that's Kepler's third law. Taking what we just did and taking it one step further, looking at multiple bodies going around the same large body. Application 4, the orbital speed with a single satellite of radius r, going r around from the object. This one we've looked at before. We simply know that v is the square root of gm over r. That's another one of our radical gamer solutions. Application 5. What if I have, and this is fairly common, a binary star system. I've got 2 stars, and they're going around each other, but they're going around a common center of mass. What does that look like mathematically? You can see this is for one of the stars. Sigma f equals mac, but here are the 2 stars, and here's the center. Let's call this the distance r. So what is the force? Well, the force is gmm over 2r squared. The force is given over this distance from here to here. But for this, and this is v squared over just plain r, because this is what it's going around, this common center of mass. Right? If these are of different masses, it gets more complicated, as you can see. And so when we solve this, right, the m's cancel out. So let's write this out. Gm over 4r squared equals v squared over r. That cancels out with one of these. And then v is just the 1/2 the square root gm over r. Application 6. So now if we have a 3-star system all going around the same center of mass, we have to do this in a similar way, except that the forces, right, it's not this radius. You've got to use some trigonometry to figure out that distance. But it works the same way. And you end up with a different answer. V is the square root of gm root 3 over 3r. Okay. If you have a binary satellite, application number 7, then again, same thing. Now you've got 2 forces there that are pulling on it. And just add up the forces, mac. So here you've got the mass of the satellite times v squared over r. So to review, the Earth is in elliptical orbit around the sun, the semi-major axis versus the radius, those types of things. Aphelion is where it is farthest from the sun, and the perihelion is where it's closest to the sun. And there's a relationship that exists between these lengths. Radius, or the distance at the perihelion, plus the radius at the aphelion equals 2a. 2a is the semi-major axis, right? This is the distance from one end of the ellipse to the next. And this is sometimes used to calculate eccentricity. So the eccentricity of an ellipse is given by this. E equals 1 minus RP over A, or RA minus RP over RA plus RP. And so for a circle, this is 1. Because in a circle, the radius at the perihelion is equal to the semi-major axis. Sorry, so eccentricity is 0. Perfect circle, eccentricity is 0. The highest eccentricity you can have then approaches 1. It can't actually be at 1, but it can get close. So we're on to the last page here. Satellites, orbits, and kinetic energy. Right, so how does the kinetic energy work? You can see the kinetic energy is given by gmm over 2r. We get that from looking at this. And so then, if you have a planet or satellite with mass m that moves in a circular orbit with radius r, the kinetic energy and the potential energy are given by gmm over 2r, and the potential energy is negative gmm over r. Don't forget that's negative. And so the total mechanical energy is the sum of those two. Okay, and now for the total energy analysis, since the kinetic energy is half of the gravitational potential energy, and negative of that, if this is the gravitational potential energy, negative gmm over r, well, half of that, that's the kinetic energy given by this here, right? So it's half the magnitude, but it's positive. The total energy then is the sum of these two, this plus this, which is given by this black line. And this plus this would give you negative 1/2 gmm over r, which is just the negative of the kinetic energy. And that's all of chapter 13.